Hello there. Welcome to another episode of Q&A about the future of science and technology. I'm still not back in my natural habitat, so not quite as high quality setup as usual. Let's see. Let me start off with some questions that were saved up here. There's one's from Joseph. How would you think about approaching science in the future? Should we accept AI's role in future science or still pursue science without the help of AI? I have one general thing to say, which is the story of my life in science has been greatly enhanced by the idea of use the best tools one can at any given stage. So back when I started doing science in the mid 1970s, there were things like, well, there was a big scientific literature out there. How are you going to find things in that scientific literature? I used to use this thing called the Science Citation Index that was on paper. I started using a thing called Dialogue, which was an early online reference searching system that at the time was mostly used just by librarians, not by scientists. Then I started using computers to do algebraic computation, which was, again, something that was sort of in principle possible at the time, but very few people did it. And then I built lots of kinds of tools, eventually Wolfram language and so on, that really make it, that have tried to make it as efficient as possible for me to do science. And not only that, those tools let one see things that one simply could not have seen without them. I mean, my whole adventure of exploring the kind of computational universe of simple programs and so on has been enabled by the fact that I'm using computers as a tool and using Wolfram language and systems we built as tools to do that exploration. So I think the first thing to say is that if you want to do the best science, use the best tools. Now the question is, AI has come in. It's a neural net AI, so to speak, has come in. And what's it good for as a tool for science? One thing it probably isn't good for is trying to do the equivalent of sort of grinding computation, so to speak. One of the things we've learnt, this is the whole idea of computational irreducibility that I've talked about for the last, 40 years now, of there are computations where the only way to know the answer is do every step of the computation. That's something that is important in understanding how the natural world works, how all sorts of systems work, how all sorts of mathematics works. It's not something that neural nets, or brains for that matter, are good at resolving. They're good at doing kind of broad but shallow computation. Whereas what's needed and what the universe does is often deep computation, this kind of irreducible computation. So if you say, well, let's just go and solve this sort of irreducible computation using neural nets, it's not going to work. What is going to work is to take sort of lots of existing knowledge and piece it together and have the neural net kind of do the analog of sort of the statistics of the world to find things that were there, sort of perhaps in plain sight, but you needed to pull all these pieces together to get that to come out with that result. And so I think the thing that, in fact, I'm probably going to try and experiment myself in sort of using sort of LLMs and AI to do science. And it's one where I'm somewhat optimistic that it will actually work. And here's the problem that I'm dealing with. So in our physics project, we have, I think, a really good model, a really good understanding of what sort of the machine code of our universe is like. But we're describing things at a very tiny scale, maybe 10 to the minus 100 meters, this kind of thing. The question is, what effects does that lead to that might be observed experimentally? Or even more to the point, are there things that might lead to which actually have been observed experimentally, but nobody knew the correct interpretation? This is what happened, for example, with Brownian motion back 100 years ago or so now, 120 years ago now, 125 years ago now, where Brownian motion was a sign of the existence of molecules as discrete elements of matter, but it hadn't been interpreted that way for probably 70 years. So sort of the best case analysis is kind of purely by, in effect, mining what has already been done, we can learn things about sort of the consequences of our physics project and see how that relates to things that have been observed experimentally. So that's an example of something where one can potentially, I don't know if it'll work, but we'll see. Maybe it isn't there yet. Maybe it is, where one's doing essentially not quite a literature search because we don't know what we're searching for. We're trying to piece things together so that we get these kind of shards of information that together can give us something which suggests something useful. So that's an example potentially of sort of a real and credible use of modern AI in science. I think the idea that, oh, well, you can just sort of sit back, relax, the AI will write your paper for you. Yeah, people send me these now. It's really tiresome because it used to be the case that if you get something which is some piece of apparently technical information, just from the almost texture of what you see, you can get some sense of what was involved in making it. Was this something where somebody had to do a lot of complicated mathematical calculation? Was this something where somebody had to do careful computer simulation? Was it something where somebody had to carefully work out sort of almost philosophical arguments? You could get some sense of that by looking at almost the texture of the document that was produced. But if you produce all those things with LLMs, they all kind of look the same, and they have, elaborate formulas, and they have elaborately written text and so on. And it takes real effort to understand, is there something to this or not? And that unfortunately is one of the things that's about to happen, I think, very big time in science. It's just a large fraction of papers being written by LLMs. Now, sometimes the reason will be, well, the person who wrote it wasn't a native English speaker, the grammar wasn't very good, so they had the LLM clean it up, so to speak. And that's a perfectly good use case for LLMs. I mean, I certainly use LLMs to do translation from between languages and things like this, and they do quite well at that. But there's a fine line between that and, oh, well, the LLM just made up my paper for me. And I'm not, I think that will end up being, the undirected tool, so to speak, is pretty useless. The intelligently directed tool, so to speak, can be incredibly powerful and valuable. And that's certainly been my experience. And I certainly expect that sort of AI is another usefully directed tool. Now, I have to say, I've used kind of sort of mostly the previous round of AI technology in a bunch of places in doing science. So, for example, one of the things I've been interested in doing is looking at a wide spectrum of different simple programs and saying which ones do something interesting. It's kind of like what you might do if you were doing astronomy and you're looking at lots of different stars and so on. You're asking, where are some anomalies? Where are some things that don't look like every other one of the last million stars you looked at? And so I've used essentially feature space plot in Wolfram language and related functionality, anomaly detection and so on, to try and process automatically millions of different cases to try and find ones that might be interesting, so to speak. And by interesting, I'm using the fact that my own personal kind of visual system, its definition of interesting is probably not so far away from the definition of interesting that the AI got from having looked at lots of human selected images and so on, that was its training data. So I've used that a decent amount. I would say that it's not something where I would say, wow, this is it's dramatically different from what I was doing before, but it is somewhat more efficient. Maybe I can process a factor of 10 more raw data than I would otherwise have done. It reminds me a lot of a thing that we do a lot for Wolfram Alpha and for Wolfram Language, which is data curation, where you're taking sort of data from the world and you're trying to validate it, organize it, make it so that it is systematically computable. That's something we've been doing for several decades now, sort of taking in information about the world, whether it's about chemicals or cities or movies or animals or whatever, and trying to organize it to the point where it becomes systematically computable. And one of the things that's been interesting is the extent to which AI and LLMs and so on can help with that process. And the answer is they can help, but they don't solve the problem. They help by maybe a factor of 2, which is very worth having. And, we're very happy about it. But it's not like one goes from you can't do it to you can do it. It's always with AI and machine learning and so on. it's always the big issue is sort of when can you find a use case that really works, and when are you pushing it into something where it isn't going to work? Things where you do precise, irreducible computation, they're a bad case for those kinds of things. Situations where you're kind of sort of foraging through a lot of material, and where if you surface anything reasonable, it's a win, that's a good case. So it's like if you're doing ranking of search results or something like that. If in the top 10 search results, there are two that you really, really want to see, that's a win. Even if there were three others that were kind of and shouldn't perhaps have been there, it doesn't matter, because the thing you're trying to do, you get a win just by the things having been surfaced at all. And that's kind of what I'm hoping might happen with my efforts in using AI to study experimental implications of our physics project. So, you know, is science worth pursuing still? Absolutely. In fact, I would fully expect, as kind of, I would say that the story of having the computational paradigm applied to science, going from X to computational X for all fields of science, that's only partway through being done. I mean, I've spent the last 40 years trying to build essentially the infrastructure to make that possible, build our computational language, build a language that allows you to express yourself computationally. And we're seeing a lot of places where that's being used. I myself end up using it a lot. I feel like at some level there's too big a gap between what I've been able to do with that and what other people have done with it. I would like there to, in a sense, to be less of a gap, because we put all this effort into building these tools and making them available to the world. And while I view myself as sort of customer number one for these tools, and the reason I think we can build good tools is because, well, at least I'm really using these tools, so I want to make sure they work well. But in a sense, it's been great that I'm able to do lots of science with these tools, but many more people than are could be doing science at the same level of efficiency and effectiveness that I've been able to do. And I think there's a huge room to there's huge opportunity for expansion in that direction. And in general, in taking kind of the computational paradigm and applying it to science. That's different from the story of AI. The story of AI, I think, is a little bit more of, right now, as I see it, is a little bit more of a kind of icing on the cake story. It's not, the main story is this kind of computationalization of science. Now, one thing that's been an interesting piece that is sort of an AI-related thing, this Wolfram Notebook Assistant that we introduced a month or so ago now, is an interesting intermediate case, because what the Notebook Assistant does is it allows you to have a conversation with it in natural language, be pretty vague, but it will try and pull your vagueness into something computationally precise and actually write Wolfram language code, express things in computational language, and then be able to do computations from them. And I have to say that we're right at the very beginning of being able to use that. I think that computational X for all X becomes much more accessible to a much wider range of people as a result of the Notebook Assistant technology. And that technology is based on LLMs, although it has a lot of other stuff in it that's based on both our technology and our computational language, and also things like the documentation for that we've developed over the last 40 years or so. And that's been important. The things that explain it to humans are also things that make it accessible to AIs. So I think we are entering at this time, the kind of computationalization of science, the application of the computational paradigm to science is still tremendously fertile. And with AI and things like our Notebook Assistant as kind of aids to that kind of opens things up to more people to be part of the kind of the going from X to computational X for all fields of science and more. And I think it's, the analogy would be science often progresses as a result of methodological advances. So a big theoretical methodological advance was from the late 1600s, the introduction of kind of mathematics into science, calculus, and so on, and that things were slower in those times. And it was through the 1700s and into the 1800s was kind of the big application of those ideas, and a lot of kind of low-hanging fruit to be picked in science, whether it was electrodynamics or fluid mechanics or elasticity theory. All these kinds of things got built on the basis of that methodological advance. Just as later on, experimental advances let one sort of do things like build molecular biology and things like this. We're at a moment where kind of the methodological advances that I've been working on for many years for having a computational language to express things, those methodological advances kind of make things ripe to introduce the computational paradigm everywhere. And that's something that I think is a tremendous thing for people to be involved with. And I suppose, when I was younger, I used to think about what's going to happen next year. At this point, I realize there are 50 to 100-year stories. And the sort of computationalization of science is another 50-year story. I've seen it over the course of the last 50 years. I started using computers more than 50 years ago now, and to do scientific kinds of things. In fact, it must be almost let's see, are we coming up on the 50th anniversary of when I first did algebra by computer? It's probably passed by now. So it's for me, I kind of get to start to see things in slightly longer time frames, and I can say that it looks to me like the sort of ramp of exciting stuff in the computationalization of science will extend for at least another half century or more. Let's see. Well, there's a question here from Yaron asking, what do you think the future of software development will be in the next decade or so? They say, I hear very conflicting points of view from friends. Well, I have to say that I think there's a question of what does it mean to do software development? What it usually means is, I've got a thing I want to make computational. How am I best going to do it? And a lot of what's been done along those lines has not been done very well. In a sense, what I've been trying to do for a long time is to automate as much as possible that process, to go from how do you define what you want computationally to kind of make it actually implemented and running, make that path as short as possible. One piece of that path is making a good way to define what you want computationally. And that's kind of the whole story of our computational language and Wolfram language and so on. And that's sort of step one is how do you define what you want computationally? Step two is how do you make it as automatic as possible to get that thing implemented, to actually build it so it runs on a computer, has all those websites and user interfaces and all those kinds of things. And we put a lot of effort over the last 40 years into making that automation work. And within our company, for example, the reason we've been able to do as much as we have with 800 or so people or something is that we've been able to automate things. Instead of saying, well, let's have another 500 people to do this, it's let's figure out whether we can have layers and layers of automation to make that possible. And that's something we've done in the context of our computational language. Now, what's happened in the sort of software development industry is there's been sort of the idea that there's bulk software development happening, and it happens in fairly low-level languages. And it's happening in languages where the language itself is just intended to be kind of the wrapper around the raw instructions of the computer, whether it's C++ or Java or Python or whatever else. The languages in and of themselves are just intended to be sort of a raw wrapper around what the computer does. Maybe there are libraries that are available that come from different places that do specific things, but the goal of the language design has been to just sort of wrap the intrinsic operations of the computer. Now, that means that it's a lot more work to make any sort of big thing that is what you probably want the computer to do, because you have to go from that sort of raw thing, maybe you add some libraries here and there to build up this kind of tower to get to where you want to go. The goal that I've had is to make it go from the specification to what you get as efficiently as possible by us having done the work to automate and smooth out that path going from kind of the computational conceptualization to the final result. An important piece of that is how do you get that computational conceptualization? How do you actually get a thing that you've specified precisely enough that the computer knows what to do? And that's where kind of the idea of computational language, the idea of providing a kind of a way of thinking about things that leads people to be able to define things computationally, that's where that comes in. I was just mentioning earlier our new Wolfram Notebook Assistant that's sort of a conversational interface to all of this that I think is a powerful new effort in this direction, where you can really go from something which is not a properly computationally conceptualized thing, it's just words, to something the Notebook Assistant can help you crispen that up to the point where it is a computational thing that you can build something computational from. So, my feeling is there's a lot of immediate, incredibly low-hanging fruit to pick because, we just spent 40 years automating a large part of the kind of software development pipeline. And, there's certainly many people, many organizations that have made great use of that, but there's also an awful lot of software development that's really low level. That really, it's like, why are you doing this? We have just one function that just does this. There's no reason to spend a month building a bunch of low-level code that does this. We just have a function that does it. And it's, why aren't you using that? Well, what I realized about the software development industry is that it's a funny thing, because once you've built up a big industry, it has a sort of a mind of its own in terms of the way that it works. A thing that we see a lot in lots of companies and other organizations, the CEOs, CTOs, whatever of those companies, will use our technology all the time. We'll write code in Wolfram language to do things. Often not the production code, but code that sort of scopes out what should be done. Actually, it could be made into production code. It wouldn't be difficult to do that, but that's not what the CEO is going to have time to do. But the CEO's kind of workflow is, let me imagine what I want. Let me crispen up that imagination in computational language and then implement something. Okay, what is the software developer's workflow? The software developer's workflow is much more, I'll come in on Monday morning or something, and I'll have my spec for what I'm supposed to write, and I'll spend the week grinding out code to do that, and then I'll go on and do and if somebody says, well, okay, what should you write code to do next? The typical software developer will say, I don't know. I just get specs for what I'm supposed to produce. The person who is running the company or that business unit or whatever else, it's up to them to figure out what to do next. And for those people, the step where they finish the thing that they wrote in Wolfram language or whatever, and they write the next thing, it's like, that's what they're thinking about. They know how to write the next spec because they're inventing it. And so what has tended to happen is that the people who are sort of the part that needs to happen with humans is the part that involves defining what you want to have happen. The part that really right now often happens with humans and probably shouldn't is the low-level grinding of producing all that code, a lot of which we managed to automate. But yet, for the sort of vast mass of software developers, it's still the case that the job is go from spec to code. And that's something that if you did it with our technology, probably you would take your week of work and you would reduce it to an hour or two. But that's sort of not the flow of the industry of software development. And so we're still in a situation where, for many companies, I mean, there are others who've very much broken out of this, our own company being an example, where you've got to this sort of accelerated state where you're really using much higher level tools to be able to develop things, and you're not kind of grinding around in the trenches, so to speak. So, people have found that, LLMs can do a bit to help the grinding around in the trenches. To me, I don't think that's quite the right direction. I mean, that's certainly useful, but it's like, why are you writing that in C++? Yes, the LLM can help you to fill in the boilerplate, but why did you need to fill in the boilerplate in the first place? Why weren't you using a proper computational language which already had those capabilities built in? Why did you have to kind of custom write them or have the LLM fill in the boilerplate for that? So I'd like to think, but I have to say, I think the timescales are horrendously long. I'd like to think that there will be a progressive trend. I mean, I've seen it over the last 40 years, a progressive trend towards people using kind of higher and higher level thinking about computation. And we've kind of defined a data point, which is kind of, I would say, an end point of a sort in defining computational language. People have, slowly gotten a little bit of the way there with kind of other tools. I have to say, not, more slowly than I could possibly imagine. And I think that it's something where that is an inexorable thing, that using kind of the ideas of using the things that we built into our computational language, and I would say that the distance between what we've built and what other people have built has gotten progressively larger over the years. That's a thing that it's kind of intellectually satisfying, a little bit frustrating, because you see a lot of things in the world where it's like, this didn't need to be done this way. This was a lot of effort that somebody put into this. It was a total waste of effort because it would just be an immediate thing with our technology. And you see other people using the technology. You say, that's pretty cool. You were able to zoom past everybody else because you were able to use that sort of higher level of automation. But I kind of think in the end, kind of the idea of sort of software development will be a thing where it's all about computational conceptualization. It's all about defining the specs, and much less of it is about the low-level operations. I will say, in my experience, in my sort of last half century in doing computational kinds of things, back when I started, assembly language was the language anybody serious used. And I remember even in the 80s, people saying, oh, you're writing in C. That's not a serious thing to do. If you're writing a serious piece of software, you should write in assembly language. And that's a thing where it's a lot more effort to do that. Turned out in the end, it wasn't, in the end, it isn't even sensible. You can get better machine code by compiling and optimizing from a higher level language than you can by a person writing in machine code, at least most of the time. There'll be a few cases where the person can have a brilliant idea and do something better. But, so in those days, I mean, people, I should have recorded those conversations of people telling me, you can't be serious. You can't do this in C. You've got to use assembly language if you're making a serious production piece of software. And, I find that interesting, but over a 50-year span, probably a 40-year span for that phenomenon, that obviously died off. People barely even learn assembly language anymore if they go to computer science school. But still, people have not, the inexorable trend of history is towards sort of higher level computational constructs. And it pushes the difficulty in a different place. If you're writing comparatively low level code, there's a very mechanical way to do that. And maybe the LLMs make it seem like, you can do it a bit faster, and maybe you're being a little bit put out of work by the LLM because it can do that mechanical stuff too. But the real work of software development should be the specification of what to do. And that's something that more people need to learn how to do. I mean, I spend a lot of effort doing language design. We live stream a lot of our language design reviews and so on. That's an art that is in very short supply. That kind of design thinking about software and so on. And that's something which it's hard work. It's intellectually difficult. I mean, of the things that I try to do in science and other places, doing good language design is up there in terms of difficulty. But it's the thing that is really the high value thing, I think, and much of the rest can be automated. So, that will be a few thoughts about the future of software development. Let's see. I'm looking at some of the other questions that are coming in here. Well, I'm seeing Intimacy is asking, thoughts on LLM use in academic writing, including student theses and dissertations. Oh, it's a can of worms. I mean, should you use a spell checker? Absolutely. Should you use a grammar checker? Probably. Should you use computational tools to build nice infographics? Absolutely. Should you get help from an LLM in kind of writing your main argument? I don't know. I mean, it's kind of if you want to write something that's kind of the average, then yeah. If you want to get, and in the grades, like what is the average grade? I don't know, a C or something. If you're aiming for a C, then you might as well use the thing that is the average of everything, the sort of the LLM that writes the average paper, so to speak. If you want to aim for the A, if you want to aim for the, hey, that was really a creative thing, that was something fresh and new, and then be a human, so to speak. Now, let me qualify that a bit. One of the things people say is, well, will the AIs be able to come up with original ideas? It's not difficult to be original. If you're exploring the computational universe of possible programs, just pick a program at random. If you're in a large enough space of programs and it's not difficult to be there, nobody will ever have looked at that particular program before. What you're doing will be original. Now, is it interesting? Is it connected to what people have studied before? Is it something where you can kind of tell a story that connects, that makes it clear why humans should care about that? That's not so obvious. So what the LLMs kind of write essays about are things that kind of fit in with what all the essays have been written about before. The thing that, to go out and sort of on a prong and sort of randomly do something original, that's not difficult. To do something that is both original and motivated is more difficult. And I think that the kind of the role of humans is to decide, out of all the possible directions you could go in, out of all the possible original directions you could go in, which ones are worth building out, which ones make sense to us humans. I mean, it's kind of like we humans could decide to get all excited about all kinds of things in the natural world. I mean, we could, I don't know, I don't think too many people get that excited about something like the shapes of clouds. But there could be a whole science of the shapes of clouds that could end up being kind of an important thing that people reason in terms of and so on. We just haven't happened to pay attention to that. That's a big role of what people contribute, is what direction should we go in this sort of space of all possibilities. And so I think when it comes to kind of the student paper kind of thing and so on, I would say that, if you're going for the A+ contribution, then, use the human. If you're going for the average C, then use the LLM. And I think that there comes a time when, you kind of wonder, what are you trying to get out of education? If you say, well, I can just automate everything I'm doing in education, it's kind of like you've got it's like the eating machine or something that just eats for you, so to speak, or whatever it is. It's kind of like, in the end, you're trying to get something into you. And that's sort of the point of education, is to get something into your brain, your mind, that will let you go further. Well, maybe practically the point of education for some people is get the qualification so that you are kind of allowed to kind of go and do the thing that you actually want to do. I think it's an unfortunate way that the world gets set up, and it's a necessary thing probably because of just the scale of things in the world, that there are these kind of gating phenomena that you have to have done this and that kind of course to be able to be allowed to do this or that other thing. And maybe you get the LLM to do that first course for you, then the fact that you're then allowed to do that next thing doesn't make any sense, because you didn't do the first thing anyway because the LLM did it for you. So I don't know. It's a strange moment in terms of how all that stuff will work out, and what will be the and it kind of reflects back at a lot of what AI is doing to us, is making us think, what do we actually want the human condition to be like? And similarly, what do we want education to be really like? To me, an important goal in education is to learn to think. And that's a very different thing from learning the mechanical process or kind of the veneer of being able to do something. Learning to think doesn't mean not learning facts, because facts are the sort of the underpinnings of how one manages to think about things. But it's kind of like, can one not only answer questions, but also figure out what questions to ask? Those are kinds of things one would like to see, I think, coming out of education. I mean, my own effort at trying to provide some raw material for education, things like these live streams are a bit of my attempt to do that, and to take what I've spent a long time doing, which is trying to learn to think about things and try to at least provide some of the output from that effort, and perhaps show some of the process of doing that. Let's see. Intimacy comments. How many new languages do we see a year these days? It wasn't long ago when I was hearing about new languages every now and then. So if you mean computer languages, that's ebbed and flowed a bit. I think it is funny to realize that Wolfram language, now 39 years in the making, is pretty old relative to kind of the overall history of computer languages, which probably can date itself back to the late 1950s. It's funny to me that the language is so modern, yet so old in the history of computer languages. It's mainly a consequence of the fact that it's based on, I would say, very clean principles about symbolic expressions and transformations for symbolic expressions and so on, which are kind of core ideas that are sort of fundamental ideas that are really quite timeless. But in terms of kind of, oh, we need to make a new language, I think there are different motivations for doing that. And there have been times when people are like, we're now building big software systems. We need a way to organize our big software systems. Or we're now building software systems that involve user interfaces. That's where sort of object-oriented programming was very much a thing, where you've got these things on the screen and you're manipulating them, and you need some way to represent that. Or, when parallel computation, it's kind of gone up and down. It's now sort of lives in GPUs mostly, which although it's coming into other places as well, finally. That's another driver for a new generation of languages, which I don't think we're quite there yet on. I mean, I've been working myself on kind of this multi-computational paradigm, which I've learned a certain amount about theoretically from our physics project and so on, and figuring out how that turns into language design. But there are these drivers of kind of new languages. So another one was sort of the web. And for a while, Java was presented as the language of the web. And then, confusingly enough, JavaScript, which has basically no relation to Java, became sort of the language of web browsers and so on. But these are things where there's a new medium in which computation is being applied. And so it makes sense to sort of rethink a bit the kind of language structure. And I think that there hasn't been, I mean, now, I suppose you could say that some of the frameworks for doing neural net computation are sort of new languages, although they're very clearly for that particular purpose. So I think that tends to be the driver of those things. When it comes to human languages, well, we've had very few new human languages. Mostly we have the extinction of human languages. I mean, there are maybe 7,000 languages on the planet right now, and some large fraction of those have very few speakers. And a language sort of becomes quite useless when there's only one speaker of that language. It's not a good communication medium when there's only one speaker. Maybe it's a good thinking medium, but languages go extinct when they get too few speakers. I think it's a wonderful project to try and sort of keep the endangered languages alive, but it's a difficult project, and it hasn't been pursued as vigorously as one might hope. I think that the thing that there is a diversity of languages on our planet that also represents a certain diversity of ways of thinking about things, which I think it's pretty interesting to preserve. I mean, I wouldn't claim that I know as much as I would like about the ways of thinking about things represented in languages that I don't know. And I know very few languages, I mean, a handful. Out of the 7,000, it's a tiny handful. And all the ones I know are Indo-European languages, which are just one branch of all of the possible languages out there. So, but in the question of whether there can be new human languages, that's an interesting question. I mean, there was a burst of activity in the late 1800s with things like Esperanto and so on being produced, those kind of gradually died off. I suppose the fact that English has become such a broad international language kind of made the utility of things like Esperanto much smaller. I mean, back in the day, 1600s, 1700s, and so on, Latin was the kind of universal language of at least scholarship. And so that became kind of the uniformization mechanism. Now that's kind of English instead, and the need for an Esperanto as a kind of uniformization mechanism has not really been prominent. I mean, there are attempts to make new languages as a kind of constructed language kind of initiative. They tend to be at this point more art projects than utilitarian projects. I have to say, I myself have been involved, something I eventually start talking about more seriously, what we're calling our symbolic discourse language, which is a way of kind of representing computationally the kinds of things one discusses in everyday discourse. And that's a different direction. That's more a language that bridges from formalization to ordinary human language. But the idea of sort of creating new ordinary human languages, right now there doesn't seem to be all that high utility for doing that. And right now there also doesn't seem to be all that high utility for creating new computer languages until there's a different domain in which one has to operate. Let's see. Promethil says, I'm using an LLM to help me through a book on thermodynamics right now. It's nice to throw misunderstandings at it. Yes, that's a good use case. It's like, talk to me about the thing I'm reading. Or another use case I've heard from students is, hey, I was supposed to learn this week. Take this and give me a quiz on what I was supposed to learn. Those are good use cases. And I think, again, it's an important feature of those use cases is you don't have to be totally precise. It's kind of like, yeah, you give me a rough quiz, I'll get, and you roughly get the answer. You're coming out ahead, so to speak, rather than I'm going to do this precise computation and launch the rocket in that direction, and oops, the computation wasn't right. The rocket, crashes somewhere. Let's see. Just comments. LLM can learn languages in a few hours. How would you think about making humans able to learn that fast? Yeah, that's an interesting thing. I mean, it doesn't hurt that the cycle time of a computer is 1,000,000 times faster than the cycle time of individual neurons in our brains. Although we have a good 100 billion neurons, and that's, in terms of total processing power, we can still give computers a bit of a run for their money. But I think that this question about how does an LLM learn and how does that relate to how we humans learn is probably rather similar. This whole question about how do you incrementally learn an LLM is complicated. It's not well understood. I mean, it tends to be the case. You do the initial training. There's a certain amount of artisanal kind of information about kind of how you do that training and how many times do you go over the training set? Do you go over it on average once? Do you go over it on average 20 times? Do you go over the important parts more often than the other parts? Do you remind the LLM about things that it learned early on close to the end? There's kind of a whole art to doing this. That's in the initial training. When it comes to fine tuning, for example, where you're trying to add in a bit more stuff, that's a very tricky business, because you can brainwash the LLM very easily and end up with, oh yeah, it knows the thing you just told it. It kind of crammed the thing you just told it, but it forgot everything else. So there's quite an art to fine tuning, which I don't think has been really well refined yet. So what it means to teach an LLM a new language it's never seen before at a level of depth, it's a complicated thing. I mean, it's easier in the initial training, I think, than it is subsequently. Now, what I think in terms of humans learning, one of the things about learning is you have a certain framework of what you understand, and somebody starts to try and explain something to you. And it's if the thing that's explained to you fits into what your existing framework, you say, aha, I get it. If the way of explaining the thing doesn't fit into your existing framework, you're just confused. I have to say, I rather often have the experience. I was just having it in a meeting I was having just before this live stream, where people were explaining stuff to me. I wasn't understanding. There were people there the people who were explaining it were people I haven't worked with, I don't know. Um, and there are people there who I do know who've worked with me extensively. And I end up asking them, I say, hey, the thing you just heard, can you explain that to me in terms that I would understand? Because people I worked with understand something about what I understand. And that works quite well, often, at least for me. And I think it's the same sort of thing with LLMs. If you get an LLM that understands what you understand, the LLM can tell you new things in ways that you will understand it, even if it would be the wrong way to explain it to somebody else, but it's the right way to explain it to you because, somebody's explaining something to me about, I don't know, higher order category theory or something. And I know a certain amount about category theory. I know a certain amount about certain kinds of generalizations and so on. But maybe I don't know this corner over here that relies on some elaborate result in I don't know what, the Langlands program or something, which I don't know well. And, so for me, the explanation should be in terms of the things that I know, not the things that I don't know. And that's something where one can imagine that an LLM can kind of personalize itself to explain things that one knows. Now, in terms of language learning, maybe the same thing could work. If the LLM knows that, oh, you have an easy time remembering this and that, then it's going to be able to customize that language teaching to the things that you know or that you find easy to do. And there'll be things where you keep on getting confused about that, and the LLM can help you out of that confusion, so to speak. I don't know. I mean, I feel like that's probably what people who are good at teaching languages as humans to other humans do. And maybe the LLMs will be able to do that as well. But the notion of, as you, the LLM will just go blah, 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 blah in some weird, complicated way that is some kind of brain hack, and then you'll know a new language. I don't see that working. I think that our brains have only a fairly thin interface to the outside world that mostly goes through language and things like visual scenes and so on. And the only way you get to explain stuff to people is through language and so on. There isn't some sort of magic, you just flash lights in some funny way and then the person knows something. I have to say, to tell a silly story about myself, when I was a kid, maybe aged, I don't know, 9 or 10 or something like that, I had this idea that you could learn things in your sleep. And so I had rigged up a tape recorder. It wasn't so easy to do at the time, but we trivial these days with everything being digital. But I'd rigged up a tape recorder that would sort of start playing stuff that I was supposed to memorize to me, while I was asleep. The experiment was not a success. However, the confounding factor in this experiment is that I have a pretty good memory. And so the very fact that I was reading this stuff to the tape recorder, to have it play it back to me, in my easy learning while asleep type mode, meant that actually I remembered it. And, it really was the discipline of reading it once was probably what I needed in order to remember these things. And my extra kind of scientific experiment, which was a total flop, was quite unnecessary. Hence, that's just one microscopic example of the difficulty of doing these kind of human subjects type experiments. Because, the confounding factor was I just, because I read it once, I knew it anyway. But in any case, I think this whole question about language learning, there are other things like, for example, my impression is that learning good accents in languages is much easier now than it was in the past, because you can look at spectrograms and things and you can get, rather than just, did that sound right? There's a phoneme in there that I don't really recognize because I was not sort of trained in early life to recognize that phoneme, and I can't tell if it's right or not. But if I can see a spectrogram of the sound I'm making, I can see, oh, it has this little formant that goes here. That's not right. Let me say it again and let me try and do it a different way. And now I can see that I got it right, even though I can't necessarily hear that I got it right because I'm not used to those phonemes and so on. So a few thoughts there. Let's see. Bersin asks, hypothetically speaking, if an AI system has access to all the images, cameras of the world, can it think through images, videos, as if there's no language? Can it surpass human intelligence like that? Yeah, I mean, I think the thing is that our way of crystallizing thoughts, packaging them so we can explain them to other people, is to turn all of those random neuron firings that make up the thoughts into kind of packaged concepts that we turn into words and languages that we can say to other people. And when we are kind of trying to remember what we're thinking or thinking back to ourselves, we usually form those thoughts in terms of language. That's our way of kind of crystallizing all those random neuron firings into something that we can remember and we can kind of build on top of. And that's kind of the role of language for us. Now, is it possible to kind of have a thinking going on without ever crystallizing things in that way? Well, you'll probably end up crystallizing things in some way, but it might not be the way that was the sort of societally agreed set of words. So you'll see in any old, neural network system that's doing image identification, it learns how to recognize, distinguish cats from dogs. And somewhere in the middle of that neural net, it's finding features of images that are probably features, there might be features that we could recognize. There's pointy ears, there's non-pointy ears, something like that. But most likely those features are things for which we don't have words. We don't have a narrative description of those features. But somewhere in the middle of the network, it had formed a notion of features that matter. And for example, in neural nets, when we do autoencoding, when we try and take kind of the whole stream of data and kind of compress it down and have it be represented by a smaller number of bits, that's a place where we really get to see this fact that the thing has extracted certain features from its original data. And so that's happening all the time in neural nets. Now, if we say, okay, you've got the videos of the world and so on, what can you say about what's happening in the world? Yes, the answer is its way of thinking about what's going on will not be linguistic in the same sense that we humans have a linguistic way of thinking about things. It will not be something where there's a way to tap into that neural net and say, hey, what were you thinking? And get out a stream of human language. What you could at best get out is a stream of its internal representation with its internal features that were millions of word-like things that aren't words that we know in our languages. So yes, it's something where we can absolutely expect that there'll be kind of a set of things that we can think of as being thought about, even though it's not represented in terms of the narrative that we can understand. I just encountered this just last week. I wrote a rather long thing about a mathematical proof that I actually first did 25 years ago using automated theorem proving. And it's a proof of a very small, definite statement. But the proof is very long and very complicated. If you unroll it, it's like 85,000 steps long. The proof was done by machine, can be checked by machine. It is completely incomprehensible to humans. I've tried to understand it. Other people have tried to understand it. It's pretty impenetrable. Yet there's a structure to it. And in a sense, the machine understood something. And you can kind of see that the machine has certain common features that it understands. In different proofs, it understands the same kinds of things and so on. But it's quite inaccessible to humans. And I think that's the kind of thinking one would expect to have happen. Now, it's an interesting question. If you say, can you think in pictures? You're really thinking in features of pictures. And that's kind of what the inner structure of what's happening in the neural net. One thing that I found kind of fun to think about is, we tend to think in terms of language. Could we have a higher level form of thinking that was that had different sort of raw material? It's kind of like, the cats and dogs probably don't think in terms of language of the type that we have, our compositional language, where you can put together sentences in many, many different ways. Maybe cats and dogs think in terms of sort of one word concepts of, sit, fetch, eat, whatever it is. And whereas we have this much richer kind of way of composing words to make a sort of infinity of different possible sentences. And so there's a question of whether we can, for example, if we had more neurons in our brain, trillions of neurons in our brains, rather than hundreds of billions, would there be some other layer, some other level of thinking that we could reach that is beyond compositional language? And one thing that sort of I was noticing is, if you just imagine, let's say, could a cat have language like we have? Well, one problem is a cat can't talk. And, a cat also And if you say, well, okay, why don't you just type? Well, yes, in principle, a cat with big keys, can use its paws and it can type something out, but it's very inefficient. And so even if in principle the cat could use language and it wouldn't have the machinery to be able to talk like we talk, so to speak. Well, if you look at us, if we say, let's communicate in pictures, well, we don't have the machinery to make pictures easily. Yeah, we could draw some sketch, but it's going to take us a couple of minutes to draw the thing, whatever else it is. It's a very inefficient way to communicate. Of course, AIs do have the ability to make images almost instantly. You can have an image generation AI, and you can have something where that becomes a medium that is sort of could be used for communication because it is instantly generable. And you could even imagine a situation where if we humans form mental images in our minds, which we can't necessarily immediately describe in words, if we could somehow tap into our brains and extract what we needed to form that mental image, that we could all be going around with little displays where instead of talking to you all, it would just be me hanging out here thinking about mental images and displaying those mental images as my form of communication. And that's sort of a fun thing to think about. I'm not sure I've thought it all the way through. To what extent, if we were communicating in pictures, so to speak, what that would be like, and would we end up eventually forming sort of linguistic structures of the kind that we do? Because one feature of our linguistic structures right now is they're very one-dimensional. They're very sequential. Language is very sequential. Images are obviously a two-dimensional thing where we can kind of examine the image in any order we want, rather than just having to listen to the words as they come in. Let's see. Uh, Maybe a few more things, and then I have to run off here. Um, 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 okay, 10x is commenting. Current AI models are very good at creating natural images of people, but totally fail for electronic circuits. That's kind of interesting. I'm not very surprised because it's like, can you put together math that really works? Can you put together a circuit that really works? These are things that require sort of deeper computation. Can you put together a picture that more or less looks like a person? Yeah, it's interesting. I wrote something last year about was it last year? Yes, last year, I think. Um, about mental images of alien minds, talking about kind of the kinds of things that an AI or a modified AI can come up with as images. And indeed, kind of just scanning through all the kind of the possible images from the alien mind, you get to these pictures where you say, you're scanning through lots of these pictures, and you as a human pause because you say, that looks like a picture of a face. You look at it in more detail, and it's a very impressionistic picture of a face. But we kind of glommed onto it and said, that looks like a face, because we're very attuned to faces and so on. And so that's a thing where I think, it can be quite wrong and still read to us like a face. If it's quite wrong and it's an electronic circuit, then it's just not going to work. Just like there can be a piece of math that kind of looks more or less right, like an LLM written academic paper or something, where it looks more or less right, but where when you really pull it apart, it's like, this is total nonsense. So it's interesting. I didn't know that. It doesn't surprise me very much. I think that the challenge there is, can you have raw material for that electronic circuit so that you can take those blocks, those kind of large linguistic blocks, and have the LLM put those together in a way that makes sense, and that naturally those blocks are forced to be valid ways of being connected and so on by the nature of the blocks and so on. I'm not sure about that for electronic circuits. Let's see. Okay, Twitch asks, how would you think about copyright, trademarks, and other intellectual property in the age of AI? Oh, what a giant can of worms. I mean, it's, well, let's see. Um, trademarks, I haven't thought so much about that. Copyright is much more well picked over for AIs. Maybe we talk about copyright first. So there are different kinds of things. Like there's a question, if you prompt your AI to write the next great American novel, but the whole novel is written by the AI, where does the copyright lie for that novel? Is it something where you, as the wrangler of the AI, can say, I am the one who should have the copyright for this or not? If your prompt was write a great American novel and the AI wrote a 50-page document, it doesn't quite feel right that you should have kind of the ability to say it's mine, it's my creation, et cetera, et cetera, et cetera. On the other hand, if you like for example, one thing I've encountered quite a bit is if you're studying, all possible programs or something, and you're going through all these different programs, and you pick out that 1 in a million, one in a thousand even, that has some particular property that you find interesting, that feels much more like a thing where you really contributed. It's just like if you take a photograph, it's not like you pick every single pixel, but you pick the framing of the photograph, the choice of what to photograph, and so on. And so that feels like a thing where there was really human input. So I think the place one has to start, I think, is how does one feel that it makes sense? And then sort of from a societal point of view, it's kind of like, why do these kind of protections exist? They exist in part to encourage the people who are making things to bother to make them. Because if everything they made would kind of, they would never get any benefit from it, it's like, well, why am I bothering, so to speak? They might bother because they just find it fun to make those things, even though there's no sort of protection against other people going using them. I mean, certainly for things like scientific ideas, there's no kind of none of the standard forms of intellectual property protection. There are other kinds of protection one can imagine, but none of the sort of standard forms of intellectual property protection are directly applicable to that. There are other kinds of protection one can imagine, so that's a thing where you have to enjoy doing it for the sake of doing it, because there's no expectation that it's yours to hold, so to speak, for the future. But so in the case of I just noticed a comment here. How do we know from Lens Manic? How do we know this is actually Stephen Wolfram? It could just be another oracle trained in long answers. Yeah, it's a good question. It's a good question. How do you know it's the real thing as opposed to just a bunch of pixels? And then how do you even know that you're the real thing, so to speak? I mean, in other words, it's a very complicated mess as we think about kind of the bot of me and kind of, a moment when sort of let's imagine that, I had little augmented reality display type thing, and the bot of me was saying every word I should say. Is it me? Is it not me? If you go more extreme and you give me a neural implant or something and you're exciting my language center and that's making me say the next thing I'm going to say, is it me or is it not me? Is it me because it was trained by my, corpus of utterances, or is it not me because there's a machine in the middle there? Is it not really me because this is transmitted through, the tubes of the internet, so to speak, to get to you all? Well, I think we have a common sense version of this that says kind of it's me if it sort of originates somehow, if the things I'm saying somehow originate in my mind, my brain, and in the current state of everything, humans are unique, so to speak. There's no kind of identical clone. If it was a digital me, there could well be copies of the digital me, many copies of the digital me, and it would be much less clear to say it's the me rather than me number, the me too, so to speak. I think, but by the way, in terms of the intersection of this with intellectual property, oh boy, that's complicated. I mean, this question of the bot of me and sort of the thing that kind of can imitate what I might say because I've said similar things before. The thing that sounds like me, there's sort of a trademarky trade dress type character to the to sort of the does it sort of seem to be me in the sense of my, I would say, almost brand or something, or does it seem to be me in the sense of my intellectual content? It's slightly different kinds of things, I think. But back to this question of under what circumstances, kind of, how much lever arm can you get from your computer, so to speak, and still have it be your arm that is sort of the thing that is the thing creating what you're creating. Now, in the actuality of things like copyright law, there are particular tests about, what was the thing, how copied was the thing, how much effort did you put into the thing? It was a famous case that went to the US Supreme Court many years ago that, a phone book that was sort of almost mechanically compiled could be subject to copyright. These things are, that was the opinion of the judges at that time, so to speak. And that's the way the precedents work. Whether that will always continue, I don't know. But that's the fact that a mechanically compiled thing can be something that has, and I think, again, that's a complicated story because by the time you can mechanically compile the thing, you have to have built a whole structure to get to the point where you can do that. It's not something where you just sort of say, well, if it is something where you just press a button and it all spews out, it feels different from the fact that, you built a company that was assembling phone books by doing this and that and the other and collecting surveys and doing all these other things, which, albeit mechanical, not having any kind of creative flair, nevertheless, you had to have an infrastructure that you built to do that. And it feels a bit different if you just press a button and do the write me a great American novel and out comes the whole novel type thing. Now, a different issue is the question of all the material that's already been produced and how that should be, could be, whatever, ingested by AIs, either for and is that ingestion ultimately for the good of the world or not, or how does that work? A common precedent, is things like music, where it could be the case that every piece of music which is copyrighted by somebody is like you just can't play that piece of music. But eventually, I don't know when it was, 1960s, maybe 70s, it was kind of the structure built up where you can play it, but and nobody's going to tell you you can't play it. But there's a whole mechanism for collecting royalties from it being played, going back to the originators of the creative, the copyrighted thing. And one can imagine something like that happening when there's sort of public good to having sort of all these things be ingestible by AIs, but yet sort of one still has to induce the humans at the beginning of the chain to produce more stuff. If the humans just say, anything I produce is just going to be eaten up by the AIs and it's not worth me bothering, that's a bad situation. It's bad, sort of societally bad. It's better if there's some feedback mechanism. How that exactly gets built, I don't know. And, there's also the question of when sort of under what, it's a complicated thing because sometimes, like a lot of stuff I write, for example, I write it because I like writing it. I think it's interesting to put it out there in the world. I'm not, if the AIs eat it up, I'm happy for that. It's not something, but it would be a different thing if I made my living writing, novels or something, or writing even nonfiction. If I made my living doing that, I might feel differently about the AIs just eating it up, so to speak. And I think there's sort of a question of, does copyright law as it now exists, what does it say about what the AIs should be able to do under, there's this idea of fair use. If you're making only sort of mild use of something, it's not sort of explicitly copying big chunks of it, then it counts as something that's sort of a fair use, because otherwise, what would be the point of having the thing out there if nobody could even read it and quote a sentence from it or whatever else, or it would be, and so the question is whether an AI ingesting it and sort of looking at it once, is that fair use or not? And I think that's a complicated question, and it sort of boils, you can, in terms of current law, I'm sure it will break down differently in different legal venues and things like this, because it really is a very detailed question of what exactly did the AI do? Did it, take a copy of everything that it saw and then ingest it? Well, the very act of making that copy might create a problem in terms of the traditional sort of formulation of copyright law. Or did it merely kind of glance at it in the way that, like a thumbnail of an image might be a glance at an image? What did it do? It's, I don't know. I doubt in the end that the current structure of copyright law and so on will be successfully kind of adapted to this. It's something which requires kind of a bit of a rethinking. And I think there are a lot of interesting questions about sort of when do you have something which is fundamentally different from, when does the thing that comes out, when is it fundamentally different from what came in? I have to say, I think my concept of computational irreducibility is not unimportant here. In other words, if you take a thing and you just make a straight copy of it, that's a very computationally straightforward thing to do. And there clearly wasn't a lot of sort of the copying process, didn't take a lot of thinking or computation. On the other hand, if what happened was you have some input and then grind, you do lots and lots of computation, and then out comes something different, then that's a different story. Now, what's interesting there is that computation in the past, when copyright law was first formulated, that computation had to be a human brain. That was the only way you would go from the input, grind, make the output. That was human brain there. Now it doesn't have to be a human brain. Now it can be a computer. How does that change the calculation of whether that thing that went on in the middle was significant or not? Now, interestingly enough, for example, when we think about something like Bitcoin mining, the whole story of Bitcoin mining is doing that irreducible computation. In fact, one might guess that the person who invented Bitcoin was aware of the things that I had written in the 1980s about computational irreducibility, and that had, even though if somebody had asked me, would these ideas about computational irreducibility and sort of the theoretical ideas along those lines, would that turn into giant Bitcoin mining farms? I would never have been able to imagine that. But nevertheless, it's sort of interesting to realize that that's a case in which sort of irreducible computation is being used as a way to kind of make a statement of value in some sense. And so I would say that in terms of thinking about things like sort of how much, what was a real activity that generated something new as opposed to just being a simple copy. I think it's a similar kind of thing about irreducible computation. Now, the real question, which sort of becomes, I would say, almost a policy question, is that irreducible computation. It can happen in a mind, in a human brain, or it can happen in a computer. What's the trade-off? If it happens in a computer, does that not count? Well, or is it the case that if there was enough grinding done in the computer, just like with Bitcoin mining, that somehow that in and of itself would constitute a valid sort of way of having generated value that was sort of copyright-like value? I'm not sure. I think these are sort of interesting things, and I hadn't actually formulated it quite this way before, that it's sort of the trade-off between the sweat of the brow, human brow, of sort of grinding things through the mind versus the computer and how that trades off and so on. All right, well, let's see. Maybe I should try and let me see if I can think about anything to do with trademarks and the world of AI. That's a funny one. I mean, I think the thing about trademarks, unlike copyrights, is that it really has to do with their sort of use in the world. And so if you have an AI come up with your next great product name and you start, advertising your product and doing all these things with your product, and people come to know your product by that name, it doesn't make any difference where the name came from. The structure of trademark law doesn't distinguish, did you get that name by, like the Kodak name, I think was sort of a randomly made up word. But that doesn't in any way, in fact, it increases, if anything, it increases sort of the uniqueness of the word. And it doesn't, the fact that oh, there was no human involved in making it up, it was just a random jumble of letters, doesn't really affect kind of the trademark story. Now, another interesting question is if an LLM starts yakking about trademarked things, and you kind of there, this is a fun scenario. The LLM kind of you're putting something on your website, and it was written by an LLM, and part of and somehow the LLM is using a bunch of trademarked terms, and it kind of you end up with a situation where kind of it looks like you're presenting things as if the LLM can present as its own, so to speak, things which are sort of the trademark terms of some particular entity. Now, what's the story there? I think the story really is how are you going to use that LLM generated stuff, and it's kind of on you. But if it was kind of the LLM fighting for itself as an independent entity, which LLM, AIs are not at this point independent entities. I mean, that's an interesting coming issue that right now, every AI kind of has an owner. It isn't the case that there are AIs running around that are truly autonomous, where it's like, look, nobody's responsible for this thing. That's a thing where you're in the current state of things. The AI is running, it's running on some computer, et cetera, et cetera, et cetera. I've certainly imagined, it's kind of a fun thing to imagine, that you put out some bot out there and it's living in some blockchain, for example, and it's in a situation where it's somehow living in a at best collectively owned kind of environment where it doesn't have a definite owner and where it detaches itself from all ownership. So it is owned by, I don't know, in some simple-minded way, it's owned by an LLC, and the LLC is circularly owned by other LLCs. That doesn't quite work. You can't quite do that. But imagine that you could somehow have this thing be an unowned object that has no human owner. I mean, there are some things in the world, like, I don't know, I think most birds flying around in the sky are not owned by anybody, except in England, where the swans are all owned by the king or something. But most of the time, I think aren't the eagles in the US owned by the government? I'm not sure. But I think there are unowned things in the world, and the question is when a bot becomes an unowned thing, and it starts doing, it starts going around and presenting itself as sort of the trademark owner, or presenting itself as if it is the source of some particular kind of trademark thing. What then happens? That's a can of worms that has to be left for another day. I think that this concept of the autonomous AI that has its own kind of that is its own legal entity, just like we've gone from the notion of individuals who own things to incorporated entities, corporations that are as if human, but they are actually not humans, they're corporations. And one can imagine a similar sort of step as one gets to the AI that is its own thing, but still corporations. Well, even then, sometimes nonprofits and foundations and things don't have owners as such. They're sort of responsible to the government in some sense, and maybe one has a similar structure for the unowned AI. I'm not sure, but those are fun questions. I haven't thought about them properly. They're good things to think about, but and I need to go off for to deal with some other things. But thank you for lots of interesting questions. This has been fun for me, at least. I hope you all have found it interesting, and look forward to chatting with you all another time. So for now, bye for now.